not trying to, cause attrition or, it's just an opportunity for you to review the material and see what you need to review, things you don't know. Really, at this point in your career, it's graduate school, it's an advanced course. We're not trying to trick you off or anything like that. There'll be no surprises. It'll be straightforward, very relaxed. Nothing to get too worried about, all right? I mean, you should study, you should review your notes, of course. Well, basically, we're just here today to take questions and review anything you'd like us to review, so ask away. All right, well, I guess we're done. Oh.
Could you go through question 3 in the practice problems?
Problem 3 in the practice problem?
Yeah.
Sure. All right, so problem 3 of the practice problem is this. We have a discrete distribution that looks like this. Let's say, I mixed it up to say it's 3, but they're discrete. So there's a certain weight on each of these pi 1, pi 2, pi 3 that adds up to 1. The first thing we say was that sample size is large enough for them, small enough for density, mode clustering will exactly be these nodes. So first of all, what are the data going to look like? So let's put the weights here, pi 1. Oh, again, I'll just pretend there's 3 of them. So the data you get are going to be all A1s, A2s, and A3s, right? It's a multinomial. So there'll be some number, N1 of these, let's say N2 of these, N3 of these, where this vector, maybe I shouldn't use 10, let's call them Y1, Y2, Y3. See, what is the distribution of Y1, Y3, Y3? Well, that's the number of A1s, A2s, and A3s. Yeah, it's multinomial. With the probability vector. And so the kernel estimator looks like this. Really, we can break the sum down now. There's only 3 types of x's. They're either equal to x1, x2, x3. So we get, and there's y1 of these. So I get, let's say, y1 over n times 1 over y1. And these are the ones where x are equals to a1. And so on. So this is, in other words, I'm just taking all the kernels here together, and the fraction of those is y1 over n. And then there's a whole bunch of them here, and a whole bunch of them here. Sum over the second group, and similarly with the third group. So there's really just 3 functions we're summing together. We're just taking a weighted sum of this, this, and this. And you notice I said to make it easier, I said assume the kernel has bounded support. So when h is small enough, these don't even overlap. So what have I got? I've got a fraction of these y1 of exactly the same function, all centered at a1. They don't even overlap with these, which is there's a fraction of these, and then there's a fraction of these. So I hope it's clear now that as long as h is smaller than the distance between the a's, that there's exactly 3 modes, one at a1, one at a2, one at a3, because each of these functions if I call this function, k1, k2, k3, is a symmetric function maximized with a1, a2, and a3. So as long as h is small enough so that the kernels don't overlap, so these are just three separate kernel functions now. And why does it say for n large enough? Well, the only time it would fail is if there was 0 observations, right? But if n is large enough, we know that the minimum number of observations will be positive eventually. We can make that precise with like bookings involved or something like that, but we didn't do that yet. But I think it's just intuitively obvious that if I draw from a multinomial, and if n is large enough, eventually the minimum of the y will be positive. So once the minimum of the y is positive, and once h is small enough so there's no overlap, then the kernel density estimator literally consists of a single kernel here, weighted by this, a single kernel here, and a single kernel here. And show that k-means clustering will also return the same thing, as long as k is at least as big as m, the number of components. So again, let's draw this again. Have a discrete distribution. Let's again assume that n is large enough that there's observations from each of the three components. So if we had done concentration of measure, maybe I would have asked you also to prove that for n large enough, this holds probability 10 to 1 or something. But I think that you can see that that's intuitively obvious. So if I take k-means with k 3 or bigger, then I claim you're going to get back these things. So intuitively that should seem obvious. So if I take k equals to 3, so now let's look at the data again. The data are going to look exactly the same, except instead of being pi 1 and pi 2, let's call the proportion here the observed proportion pi 1. What is the value of the k-means criteria if I put a center at each of these? So let's do k equals to 3 first. It's 0. You can't get any smaller than 0. So therefore, a solution to the k-means thing is to set each of these to be equal to a 0, and you get exactly back A1 and A2 and A3, right, as the centers, right? So in other words, remember we're minimizing clear that each one of these observations falls into one of these three categories. So if I pick C1 equals to A1, C2 equals to A2, C3 equals to A3, that wherever the data point falls, it's equal to one of them, so that it achieves the minimum of 0. So this is 0. So therefore, picking A1, A2, A3 as the clustering is a solution. But that's also true if K is 4, because I can just pick this one, this one, this one, and take the fourth one to be equal to any of the previous ones, and it's still 0, and you can't pick it any lower than 0. Yes?
In this case, regarding the initialization, if we use k-means plus plus, we'll get the exact thing, right? Because picking up the same point will have probability 0, because it will be on the same.
Yeah, I mean, it's kind of a degenerate case, right? So, although you wouldn't even need k-means plus plus in this case, right?
But if you don't use that, then couldn't you have your means in like one of the modes would not by mean?
It's true. You're saying with the fourth one here without any.
No, even with only 3, you
Oh.
can have 1 at A1 and 2 at A2.
No, that's not going to minimize it then, right?
Yeah.
Oh yeah, okay.
Right. If I put 1 here and 2 of them here, then these are going to have positive value, and so this will not be equal to 0. Will not be a minimizer.
I think the confusion is coming from the difference between the k-means criterion and Lloyd's algorithm. So they're saying if you run Lloyd's algorithm,
So I'm talking about the actual solution to k-means clustering.
Okay.
That's right. If you ran Lloyd's algorithm, you could get unlucky. You're right, and I would pick 1 here, 2 here, and maybe get stuck there forever. Although it's not clear, you would get stuck there.
Yeah, you can construct initializations that is
Yeah, probably if I move this far enough away and something
Yeah,
like
yeah.
that. Yeah.
has some.
So yeah, I was not so let's all keep in mind the difference between k-means, which means to minimize this thing, and Lloyd's algorithm, which is an attempt to minimize this thing. It doesn't guarantee to minimize. Right? So I was referring to the actual minimization.
You can make that clear on the midterm too, if we,
If you see k-means on the midterm, assume it means the actual minimizer, unless it says otherwise. Yeah.
Talk about the demo rhyme spaces, just like
I'll turn it over to this guy.
for intuitions about what the objects are about.
You guys?
no, sorry.
He wasn't even paying attention. No, he was off duty.
Demoler Rhine? Just in general, or?
Yeah.
Okay.
If you break it in half, it'll write that. That's what I was.
Except the trade. So for smoothing splines, we had this representation, right? Is this, are you happy with this, or do you want to see where this came from also? I was asking you, sorry.
I think that one's okay.
That's okay. Okay, so, yeah, I can just back up for 1 second and just very briefly show that came from. So we had, I don't know if we called it, you know, I can't remember exactly, but we have, we have this representation just from writing it as that P lines problem, where B was the basic matrix, it was n by n. And this was a penalty matrix that came from, its elements had like the basis functions taking their derivatives and integrating their products. But this just came right out of the fact that we can write smoothing splines that was generalized ridge regression. And then we did a little bit of algebra to manipulate this into the form I plus lambda k inverse y. And here k was equal to, I think, B transpose inverse omega B inverse. Do I have that right? Somebody has the notes in front of you? Is that right? So from here to here, it's just a few manipulations for the matrix multiplications. But the reason we did this is because we wanted to essentially understand the action of smoothing splines as a linear smoothing. And so that the way to understand that action is through what we call the Demoler-Rhine spaces. So we did the following. So forget the specific form of K. That was just to convince you that this was true. We took an eigendecomposition of K. So there's a symmetric positive definite matrix, so we can do that. And so let's write its eigendecomposition like that. And so U has orthonormal columns, and the diagonal elements of D are non-negative. And so what we ended up doing was we expressed this fitted value in terms of the eigendecomposition of K. And so we can just write right here, if K has this eigendecomposition, then I plus lambda K has the following one. It's going to look like U I plus lambda Q squared E transpose. I haven't taken inverse here yet, but yeah, you're right. And then that holds just because U has orthonormal columns and also has orthonormal rows. It's matrix. So U transpose is the identity. And then so if I take the inverse of this, then that's its eigendecomposition. This is still a diagonal matrix. So I'm just going to invert each one of its entries. So I can actually just write that like, I'll leave it like that actually. Okay, so that means that y hat is equal to u times I plus lambda d squared inverse u transpose y. And another way of writing that, remembering that this is diagonal, is like this. It's the sum over all of j of uj transpose y times uj all over this diagonal element, which is 1 plus lambda dj squared. And so we're almost there, kind of understanding the action of smoothing spline operators, of the smoothing spline operator, but we have to understand something like what are the UJs and what are the DJs. And then once we understand those two things, it kind of tells us the story about what's happening. The first thing to notice before we do this, though, is that if lambda is 0, then this thing just looks like u times u transpose y, or uj transpose y times uj, take the sum of that. That's just doing regression of y onto the columns of u. That's what I get by doing regression of the columns of u, because how do I regress y in the columns of u? Well, I would do the following. I do u times u transpose u inverse u transpose y, but since u is orthogonal, that's the identity. So regression of y onto the columns of u is just u transpose y, which is uj transpose y times uj. And so the way I'd like to think about that is as follows. Let's think of these as the regression coefficients, beta hat. And so I'm actually going to think of this as the sum of beta hat j uj. So if I do u transpose y, it's like regressing y in the columns of u, and this is the form. So what's this then? This is like taking those regression coefficients and then shrinking them and dividing by something positive. So it's like I'm regressing onto the columns of u, but I'm shrinking the regression coefficients. Okay, so what we got from homework 2, I just looked at the solutions actually, they're very nice solutions, I'll take a look at them, is that we actually computed those u's, and we showed that those u's looked like, as a function of the index, so if I plot the components of u across their index 1 through n, they looked like smooth functions. So actually 2 of them, if I'm talking about cubic smoothing splines, 2 of them are linear, and then they kind of had different behaviors, and they got more and more wiggly. So here, I'm just plotting, say, the first 5 u's, maybe that's what they look like as a function of their index. So to fit y, if I'm just doing regression on u, then I'm basically constructing it as a linear combination of these basis elements, these functions. But what smoothing splines do is they actually take those regression coefficients, like these ones here, and they shrink them by a factor. And that factor, it's actually it's different for different regression coefficients. So the shrinkage factor, right, the weight multiplying uj is actually its regression coefficient over 1 plus dj squared. And so we notice that if dj is large, then this is a lot of shrinkage. And if dj is small, it's not much shrinkage at all. And so what ends up happening is, the ones that are really wiggly, like this guy, again, as you would have, you see from looking at a concrete example, like on the homework, the wiggly ones have large DJs, and the smooth ones have, so say this smooth one here, this has a small DJ. And actually the ones that are linear, they have 0 DJs. So it means that we don't actually shrink the regression coefficients that correspond to the linear parts, and the ones that are smooth, we shrink less than the ones that are wiggly. So the whole point of the Demler-Rhine spaces was just to gather the insight that it is true, or maybe we can see it from just looking at the minimization problem, but it is true that smoothing splines actually try to model a given input vector y as a linear combination of basis functions and has a preference for smoother basis functions. And that's just made very explicit with this representation. Yeah.
For the zero eigenvalues argument that we have, we say that when we look at the actual objective that we're minimizing, we have this regularization term with the integral, and that is a derivative of k plus 1 over 2 order.
Right.
And we say that because of that, we need that many zero eigenvalues. But what about, couldn't there be derivatives of higher order that are non-zero?
I didn't quite understand that. I got everything up until the last part. So that was you basically describing the solution to the midterm practice problem 2, I think.
Yeah.
But what was the last part?
So we say that this integral has to go to 0 because we are penalizing it heavily,
Right.
and so that derivative has to go to 0. And this way we say that our fitting function must be of order k plus 1 over 2, right?
Yeah, I mean, I would rephrase it by saying that
Minus 1.
if you look at the criterion, it's something plus lambda times, like you just said, the k plus 1 derivative over 2 of x squared dx. And so you know, just by looking at this, that if for whatever reason, if it happened to be the case that y was equal to some polynomial function, let's actually just say if y was equal to g, I'll call it L of xi, gl of x is just x to the L. It's just that polynomial function. If it happens that y was just the evaluations of gl, this polynomial function, for any L that's less than or equal to k minus 1 over 2, actually, for any L that's between 0 all the way up to k minus 1 over 2, then regardless of lambda, I get out the smoothing spline solution to be exactly GL, because it makes this 0 and makes this 0. And so, and that means that if I plug in this vector y into the smoothing spline operator up there, this guy, then out must come 1. Because this is the solution to this problem, and we just saw by looking at the problem directly that these things are unchanged, right?
Yes, but if, for example, we have a fifth order spline, and this will tell us that the third derivative must be 0. What if the fourth derivative is non-zero?
If I have a fifth order spline, so k is 5, so this has a third derivative has to be 0. And you're asking,
What if the fourth derivative is not 0?
that's okay. I don't understand why that's contradicting what we just said. All we've proved is that it must be the case that there are essentially 4 non-zero basis vectors that are in the null space of this matrix, or of k, because if I stick in the constant function, the linear function, quadratic, or cubic, all of those come back unchanged. And so in all of those guys, if I take y to be the constant vector, the linear vector, they're all eigenvalues, they're all eigenvectors of this matrix, is eigenvalue 1. And so that just means that k has, if I flip that around, k has 4 eigenvectors with eigenvalue 0. If the fourth derivative, if you're worried about that, you can actually construct an example where you convince yourself that that's not going to be a basis vector, because I can find such a quartic function that does not achieve a 0 in this criterion. Did that clarify your question about the basis, or there's still?
I think that was a big quit. So the eigenvectors of S form a kind of a basis, an alternative basis for the splines on which S, we can think of S as like acting in a particularly simple way. So they're like, hey, what are these days really?
The eigenvectors of k, actually. So S is I plus lambda k inverse, but the eigenvectors of k. Yeah. What are those guys? So they are polynomial functions or they actually are themselves splines, natural splines, that span the same space as, that they're going to span the space of natural splines as not the data points. And so we're just seeing that smoothing splines do like a shrunken regression on this particular basis. It's a more transparent way of seeing it than looking at this. See here, it is doing actually a regression on the columns of B, a shrunken regression on the columns of B. But what's happening here, it's very confusing because this is a dense matrix, so it's unclear how the regression coefficients are being affected here. It's not like I can tell you what's going to happen. If you told me that you did a regression on B and asked me how to explain this in terms of that regression, I couldn't explain it to you because this matrix omega is dense. And so instead of explaining smoothing splines by regression on B, which is the natural spline basis, which we kind of understand, I introduced a second basis called Daimler-Reinsch basis, which is these guys. And I can say very precisely how smoothing splines were doing a shrunken regression on them. So I just take the regression coefficients from them, and I divide by constant. And that constant is bigger if the basis vectors are more weighted. So it shows you that it's shrinking even more.
It helps to do another interesting thing, by the way, about spline. People often make the claim they'll write a spline base. You can find spline basis functions. I think Ryan had about these splines, where the basis functions look very localized. And they said that what they like about splines is the basis is localized. But it's actually not quite true, because once you finish the fit, you see that it's actually doing a linear combination of these kind of cosine-like things, which are not localized at all. So it is more transparent to see what's going on with the smooth version of that. By the way, also Ryan mentioned something that might have gone by quickly. We posted the solutions to homework 2.
Yeah.
I just got a quick question about smooth splines. The linear from regression science having aggregate interactive on basis and then having aggregate for the smoothing spline. Is that because of the repeating extent or adding?
Yeah, so it's because of this surprising fact that Larry doesn't believe that if you have a natural spline basis with, say, Q knots, and then the degrees of freedom is Q, so I need Q basis functions to represent them. So if I have knots at each data point, then I can have, and there's n data points, so I'll have n basis functions. And that will be true regardless of what degree I take. Yeah, otherwise, it would be, if we didn't use, if we used just cubic splines instead of natural cubic splines, then this B, it would have n rows, but it would have n plus k plus 1 columns, which actually would be fine. There would be nothing wrong here because I'm still regularizing. So it would be well defined, but it's just not what, we wouldn't be able to express that as a solution to a problem like this, which I think to many people is like the selling point of smoothing splines, that you can stare at the criterion in this function kind of way. Yeah.
This is an extension of Anthony's question. So say for instance we use more than a higher order polynomial, say not the cubic, but say something like that. Then k plus 1 by 2 is 3. And when you plot this basis function out, would you observe linear, you observe 2 linear quadratic and cubic basis too?
Yeah, exactly. So, so let me say one other thing, which is I don't think I ever said this in words, but you guys are hitting on it right now, is that smoothing splines can only be fit for odd order polynomials. If k is not odd, then this is not well defined. So I can't fit a 4th degree smoothing spline. It doesn't make sense. So you're right, it is really 3rd order, 5th order, 7th order, etc. Because I'm taking the k plus 1 over 2's derivative. I'm taking that order derivative. And if I did do a 5th order smoothing spline, then it would be the case that there are now 4, k plus 1 over 2, 3 things in its null space, right? And that would be the linear, quadratic, and the cubic. The constant, linear, and the quadratic functions. And so when I would draw this picture, I would basically, I'd get this linear guy, I get another linear guy. I mean, it's not really linear and constant, it's not really well defined which one I'm taking, but then I get a quadratic guy, and instead of having a small eigenvalue, you could actually have a 0 eigenvalue. So I wouldn't be penalizing at all a quadratic.
Say in the exam where we have this question, do we also need to write formulate that these function, this like from zeros to the k plus 1 over 2, other function, differentiable functions are actually expense analysis, meaning that we need to argue that they are not linearly dependent, or is it a trivial thing that we can simply say?
I think you can assume that. You don't need to prove that. And so here's a proof in case you're worried about it. Those functions are linearly independent, right? So if I evaluate those functions at endpoints, they have to be linearly independent vectors. And by the way, I just want to make sure that this is where I guess I went over this part quickly too. Any polynomial function of order 0, 1, all the way through k minus 1 over 2 has the property that if I were to observe y to be just evaluations of that, and when I solve this moving plane problem, I get out y. And how many of these are there? There's actually k plus 1 over 2 of them. That's why there are k plus 1 over 2 elements in the null space of k, or k plus 1 over 2 eigenvectors of eigenvalue 1 of that S. It's because I count all of these, I get k minus 1 over 2, and then the 0 adds 1 more. So it's k plus 1 over 2. Jersey? Sure. So should we just do problem 2? Would that help if we did? Okay. So what I want to prove is that, I don't even actually remember the question, what it was stated. Oh yeah, okay, so we had this, y equals I plus lambda k inverse y. We wanted to prove that k had a certain number of 0 eigenvectors, 0 eigenvalues. So we would write, first of all, we'd write this, just using the same thing up there actually. I was going to write an eigendecomposition of k, so I'll write it like this. And I want to know something like some of these diagonal elements are 0 for d. And just using that same argument I gave up there means I can write y hat as this. By plugging in for the eigendecomposition of k. And so what I was saying was that it turns out that, well, actually, we don't even really need that. Let's just call this S. And the following is true. If I have S u equals u, that's true if and only if ku is equal to 0. Actually, maybe just for that, it might be helpful to see this representation. Okay, what this shows is that this is, if k has eigendecomposition this, then S has eigendecomposition this. So particularly the eigenvectors of S are u also. And its eigenvalues are I plus lambda d squared. That's 1 over these. 1 over 1 plus lambda dj squared. And so for that to be 1, I have to have that dj was 0. That's all it is. So in other words, the eigenvalues of S are 1 over 1 plus lambda dj squared. And the eigenvalues of k if S has an eigenvalue 1, it's the same thing as having an eigenvalue 0. So if I'm asking you to find the number of the multiplicity of the 0 eigenvalue for k, it's like saying what's the multiplicity of the 1 eigenvalue for S. And so how many vectors does S have the property that when I hit it by S, I get back the same vector? Well, actually, the way to think about that is not think about S as this matrix and try to analyze the properties of this matrix. But remember that S gives us the fitted values from this problem. And so that's really what makes this, this much more transparent. You don't have to do any algebra or anything like that. We just say S gives us the fitted values from this problem. So which vectors y have the property that when I pass in y to this problem, the solution y hat, the fitted values, which are going to be y hat of I is f hat of xi, I just get back yi exactly. So which y I have this property? Because that would mean that if I multiply s by y to get y hat, I get back just 1. So it's an eigenvector of eigenvalue 1. And when I look at this problem, I see that if it happened to be the case that yi was just, say, g of L xi, why don't I just write it more transparent? So it's just xi to the power of L for any L that's an integer between 0 and k minus 1 over 2, then y hat I is just going to be 1 I for all I. And why is that? Well, it's because I can find a function f that makes this thing has the value of the criterion equal to 0. So it's going to be the solution. And that is just going to be the function that takes x to the L. Because if I take x to the L, it makes the loss term 0, because by definition, yi was xi to the L. And it also makes the penalty term 0, regardless of how big lambda was. Because if I differentiate a polynomial of degree less than this one, then I'm going to get 0.
This way you show that the dimension of the null space is greater or equal to k plus 1 over 2, but you didn't show that it's also smaller.
Yeah, you're right. So, so I think that was also your question, kind of, right?
Yeah, I have something based on what I asked earlier. Because of that integral, does that imply, because it is an integral of that square, that the higher order derivatives are always 0? Because if we take the integral
Yeah.
of, say, the second derivative, and we set it equal to 0 for all x, because it's the square of that, right? So it must be equal to 0 for all x.
Yeah, okay.
That implies that the higher order derivatives are also 0, right?
I didn't understand that. No. Sorry. Let me go back to Yusheng's question. I don't want to jump ahead of that first. So what I have to do is I just have to construct an example where okay, first of all, I guess I was not expecting you guys to prove that direction for this part, so you don't have to worry about it. But how you prove it, in case you're curious, is that you have to construct an example of n minus k plus 1 over 2 vectors that when I hit them by s, I get something that's not the identity,
I guess
and they're really independent.
I guess you have to show that anything that is in the null space of A can be represented as a linear combination of this.
Yeah. Yeah. That's another way to do it.
But how to do that in a functional space is still like tricky to me.
Well, I wouldn't think about it like a function space, right? Because I'm talking about the null space of a matrix. The only reason we went to function space is to avoid matrix algebra.
Yeah, but the argument is that we construct 3 functions and we get 3 vectors. And we know that these 3 vectors are actually linearly independent of each other, so they stand a null
not know that all the entire null space is spanned by these vectors.
Yeah, you're right.
So in order to do that, we have to go back to the functional space and say that these functions actually have already like spanned the entire null space in the functional space, restricted to its length because of the variation of the function.
So I wouldn't worry about the difficulty for this problem. I mean, you could, I guess the most precise answer would be that the multiplicity of the zero eigenvalue is bigger than or equal to k plus 1 over 2. So I say it's equal to k plus 1 over 2. First of all, it's going to depend on x. So you could just construct for an arbitrary sequence that say it doesn't have the property that I have any two x's at one point. You can construct examples of functions that don't have the property that when I stick them in, I get back out the result. And if you can construct n minus k plus 1 over 2 of them, then you're fine. We've shown that the answer is that there's exactly k plus 1 over 2 things in the null space. And I claim those come from the rest of the basis functions. Sure. Your question? Similar or no?
It is similar. So my argument is how to prove that it's smaller or equal than k plus 1 over 2.
Okay, smaller. That one I can do.
Yeah, and I basically have something that I need to ask on that. Like, because we have that integral there, this should imply, if that integral goes to 0, it should imply that all derivatives higher than that are 0, right? Yeah, yeah.
Yeah, I don't, but I'm not setting this integral equal to 0. I'm just saying that maybe you're confused about something that's related but not the same. Because I'm just saying that if I just plug in this function, let me plug in the function f of x equals x to the L, then it gives the 0 value for this interval.
Okay, I see.
And if L is anything in between 0 up to k minus 1 over 2, then it gives the value of 0 for this interval. I'm not saying that this being 0 implies something. I'm just actually plugging in for this function.
Okay.
This question might be a little confused, but so you look at the function of the minimization and you say, okay, what are the sorts of things where I would get that exactly yi? And you say, well, those would be the sorts of things that are lower than degree k plus 1 over 2.
Yes.
Right? And then you say, okay, then there have to be so and so many of those represented as eigenvectors in my basis, right? So how do I know that if the degree I find is 2, that I have to have exactly 2 eigenvectors in my basis of exactly that degree or lower? I mean, is that obvious or?
Well, I mean, I think it's natural. I don't want to say it's obvious, but it's natural because you're asking the question, like how many degrees of freedom or how many, what's the dimension of the space of polynomials of degree k? The answer is just k plus 1, because I can write any polynomial like this, right? Say a1 or a0 plus a1x plus akx to the power of k. And so if you just tell me that you want a polynomial of degree k, I can just pick x to the power of k minus 1, x in the constant function, and use any constants to create an arbitrary polynomial. So another way of saying that is that these things, a0 times 1, x squared, all the way to x to the k, those are basis functions, and there's a k plus 1.
Right, but we have this like jury-rig rotated basis now that we're looking at, and which is the eigenvectors of S, and how do we know that there's exactly 2 basis vectors in there that correspond to the things of degree less than 2? I mean, it seems, like you said, it seems natural.
Oh, that comes from, I mean, maybe I should just step through the logic one more time, and then if that answers your question, great. If it doesn't, you can tell me what I missed. But I want to know, let's say, how many eigenvectors S has that eigenvalue 1. Because that's the same thing as k having eigenvector of eigenvalue 0. And so I don't actually really care about the form at this point. I'm not worrying about the Lemma spaces or anything. I'm just saying that S is the operator that when you give it y, it multiplies sy and gives you back y time. So I want to know how many y's have the property that y is equal to s of y. And in fact, I just want to know a basis for that space, the space of all y's to satisfy that property. And I'm just constructing a basis by noting that those such y's have the property that in this problem, I pass them in and I get them back out as the solution.
Actually, right, for the cubic symmetric lines, it's very easy to understand. So the diagonal range basis has two like linear functions in there. So those correspond to two diagonal vectors, and they can be linearly represented by a constant and ax by these two bases. So
Yeah, sure. That's another way.
I know that from examining it,
Yeah.
but I know that because we plotted them, not because.
Yeah. So that's why I was trying to argue from just from here. Did that, what I say? That last sentence. I want to know how many y's have the property that sy is equal to y. What's the dimension of that space? It's a vector space. And I can say, well, those are the same y's that have the property that when I stick them in here, I get back f hat, a function f hat whose evaluations are just y line. And I just constructed all such possible functions by saying that, well, those functions have to look like linear combinations of these polynomial functions. There's k plus 1 over 2 of them, so that means that there's k plus 1 over 2 such y's. Yeah.
Slightly different direction. I have a question from homework 3, but I'm not sure if that's in play or not.
You could ask it. I guess I could say I have to plead the fifth or something.
Okay. So basically, it's constructing a distribution as the sum of normals with independent means in the same variance.
Okay.
Squared. So giving a chi-square distribution. And basically, it eventually asks us to construct a Bayesian and a frequentist confidence interval from some constant to infinity. And I guess I'm finding it a little challenging just because there's a third parameter in there where b is the sum of the mean squared. So it's asking for, in the Bayesian case, the confidence interval for v given x's.
Oh, no, but, so, yeah, I think it's, so if I remember, it was this, you have yi normal, and so the prior we took, just to keep the calculation simple, was flat, right? Just keep me on track here because I'm doing this by memory. So first of all, what's the posterior for the vector? Let's take the likelihood multiplier, it's,
The likelihood.
which is?
So it's just normal.
Right, so mu given y is a multivariate normal with mean y and identity for variance. But then so that's the exact posterior distribution for mu. I think the question asks you to construct the posterior for the sum of mu I squared.
Yeah.
But what is that? That's now, from the point of view of the posteriors, that's the sum of a bunch of normals. So let's write now, from the posterior point of view, I can write mu I is equal to its mean plus, let's say, delta I, where delta I is normal 0 I. That makes it normal, mean yi, variance y.
Sure.
So this is nothing other than, again, keeping yi fixed, that's a representation of the parameter of interest. But remember, yi is fixed, the delta i's are random. This is exactly a non-central Westbury. That's the definition of a non-central Westbury.
So we'd get the confidence interval, or the Bayesian interval just from the properties of the chi-square.
So now, let f be the CDF of a non-central chi-square. Express the posterior region in terms of the CDF or inverse CDF of a non-central chi-square. That's all, that's the best you can do. Now you can, it does, I said in there somewhere, you can approximate it by normal too. A non-significant chi-squared has a normal approximation, if you want a more explicit description. But it suffices for the question to express it in terms of a non-significant chi-squared. Splines are hard.
No, they're not. Wait for it.
It's funny thing about smoothing, that everybody has kind of their first look at it. So I like kernel smoothing. Brian likes spline smoothing. But we get the same answer again. If you look at our plots there. Other questions?
So we talked about using kernel smoothing, and we talked about kernel regression with various kernels, including a Gaussian kernel, and then we talked about the RKHS approach, which can also have a Gaussian regular basis. Is that the same thing?
No, they're not quite the same. So a very confusing thing is the kernel smoother, like kernel density estimation, kernel regression. And then the RKH, I'll write it down and tell me if this is how you wrote it, Ryan. Where this is the, is that what you wrote down?
It's pretty much exactly. I wrote on H sub K instead of for a Hilbert space.
So you have a Hilbert space generated by a kernel, and you use this penalty. And by the way, pick a particular reproducible Hilbert space, you get exactly back to spline, which is so splines are a special case of reproducible kernel. But you can pick any kernel you want to generate this, and yes, you can pick a Gaussian kernel, but you will not get back the estimator. So let's write down the kernel regression estimator. You won't get back exactly this, because this is putting equal weight on each point, which is not exactly what you're going to get back from the reproducible kernel Hilbert spaces, but despite the similarity. Now, I've never been able to construct an example where they look different. That is substantially different. So they're very, very similar, but they're not technically the same. And actually, the reproducible kernel Hilbert space one. So remember, what is the reproducible kernel Hilbert space estimate? I think Ryan told you, right? It's some linear combination of the kernels. Whoops. That's the estimator you get, which looks a lot like this, but it's got a particular form. These are allowed to vary the betas. That's what you're minimizing over. Whereas here, you're putting a very specific weight on each observation. And to see that they can't quite be the same, there's only one tuning parameter here, which is the tuning parameter of the kernel. But here there's two tuning parameters. There's the lambda, and the kernel itself is a tuning parameter. Nonetheless, in the standard function spaces, you get the same minimax rates. It's the same rates of convergence. In fact, there was a little bit of misconception for a number of years that if you use a normal kernel here, you have these two parameters. People usually pick lambda by cross-validation. How do you pick the extra parameter of the kernel? For many years, people said it didn't matter, you just picked anything. But there was a recent paper by Ingo Steinwart who showed that's not true, that if you actually want to get the optimal rates of convergence, you also have to optimize this parameter too. And then you get the standard rates. But so they do, it's kind of confusing because they look very similar in the same word, but they really come at it from different points of view. Numerically, the estimators might look very similar if you choose the tuning parameters approach, but they're not exactly the same.
sorry, I had a question on clustering. So it's probably a bit naive, but I remember in your notes you showed for mode clustering that the estimated modes, I guess the two norm between the estimated modes and the true modes is big OP something. Is that kind of? I was wondering if you how do you take away from that like a verbal description of the goodness of that result? Like,
Well, I guess that's a general question, right? So let's go back to estimating the mean. So a standard fact about the mean is that x bar minus mu is OP1 over root n. Informally, we just interpret that as saying x bar is about 1 over root n away from mu. It's just telling you something about how fast the estimator is approaching the truth. And so in the mode case, let's just say even one mode, I think we got OP 1 over n. Does anybody remember what it was? It was 1 over 4 over d or something?
yeah.
And you know what you see is that it's much worse than this. So it's I think d equals 1 over n, and 1 is quite slow. So, but that's always the case in sort of non-parametric problems. Estimating the mode of the distribution, the non-parametric problem. So it's just saying, you know, the way to think about it is how far is the estimate from the truth? It's about 1 over n to the 1 over 4 plus d. I don't know if that's what you're asking. Is that what you're asking?
Yeah, I think, sure, yeah.
And then the point of saying that that was the minimax rate was to say, well, that's kind of a bit slow. Can you improve on it? The answer is no. Unless you put stronger assumptions. But yeah, statisticians are very fond of writing this OP thing, and we just get used to thinking of it as, okay, that's telling us how close that thing is. And it's just a way of telling you how close the estimate is to the truth. It's a way of thinking about things.
So this is going back to science.
Back up.
But like it's actually related to like kernel regression. So like in kernel regression, we have a dependence on dimensionality, which is bad.
It's bad, sorry?
It's bad, like high dimensions.
Oh, yeah.
Yes.
And but at least computationally, it's just linear number of things. Whereas if you're like extending splines to high dimension, then you start incorporating all the customs. This computation is going to suffer in dimensionality too exponentially. Like I just want to know about the statistical efficiency, like the rate of conversion.
In higher dimensions, so yeah, I mean, I would point that to GK, but yeah. I mean, so
Right,
we have,
The minimax rate is right, or
Yeah.
this suffers dimensionality, but like is there in high dimension, is there any advantage to using splines over kernel regression?
I'd say there's less of an advantage because of the fact that you have to, like, there are multiple options for extending splines to higher dimensions. The one that we wrote down in the notes was called thin plate splines. They actually don't, the computations for thin plate splines are not exponential in dimension, but they're special. Thin plate splines have the special property that they're isotropic, meaning that if I rotate the space, the estimate won't change. So there are special types of high-dimensional spline that are, in some sense, spherical. So they are an option for splines that do not suffer an exponential degradation computation. If you use something like a tensor product, then that would be an exponential degradation computation of the function dimension. But I think that probably the most, you can tell me if you disagree, the most generic way I look at it is that in one dimension, like Larry said, all these things are very similar. I have a preference for splines because of the fact that they're computationally very efficient, more so than kernels, say kernel smoothing in one dimension. And you don't have to choose a kernel, you have to just choose smoothing parameter. At higher dimensions is probably why I think more people from CS are more familiar with kernel smoothings because they're kind of trivial to extend. You know, you just do that, you write down, take the norm. That's it. Splines get complicated. You have options on how to expand them to higher dimensions. And so those options make them more complicated and in some sense less desirable. But like we said, I think probably the thing to take away about non-parametrics in higher dimensions is actually that with the additive model, you can just treat everything as one-dimensional. And so then you're back to the one-dimensional case. And if that's a territory you're comfortable with, and I think that's really beyond dimensions 2 or 3. I think almost nobody fits full dimensional kernel smoothing or non-parametric regression or smoothing splines beyond like 2 or 3 dimensions. It's almost all additive models. What people do. And the reason for that, by the way, is that if this is there's multiple reasons. One is computational, the other is statistical. If this is the minimax rate for estimating, say, a function in one of the standard function classes in d dimensions with degree of smoothness k, then if I assume the true function is additive, then actually the minimax rate for estimating that function is back to the one-dimensional case. It's just back to 1 over n times 2k over 2k plus 1. So this is general, and this is additive. So actually, you have a hope for estimating additive functions in high dimensions. It doesn't depend on the dimension. And so it's this hope that gives us a preference to try to at least aim for an additive estimation, an additive approximation of the function. So the Gaussian process regression estimator, is it exactly an RKHS estimator, Dr. Askew? I think the answer may be yes, because kernels are very linked to covariance operators for Gaussian processes. In fact, they're both positive things. And so I'm not sure if they're one-to-one correspondence or not. Anybody know? Is this a, yeah, so yes, so the answer is yes. Yes, interesting that you asked that. So the mean shift algorithm I said is like a gradient descent algorithm, and one of the whole questions is about that. But it's been kind of more like a folklore thing. Everybody just treats it like it converges. There's actually a paper on the archive now by Arias Castro. And David Mason. And it's on the archive. And it's actually a very formal analysis of how well does the mean shift algorithm approximate the gradient. And they look at it, because you're really getting these linearly interpolated. When they look at the true gradient descent curve, and they see that all the curves, these polygonal things converge to the gradient descent curve as the balance goes to zero.
Is this proof on specific kernel or general?
They have conditions on the kernel, so it's not for one kernel, but it's for class of kernels. There is a homework question where you make a link, I think, with the makes a gradient descent.
Based on a specific kernel.
Yeah.
I wanted to just add one thing. If this is getting too much detail, I'm going to stop quickly so I'll see. But I was thinking about your question. I want to add one more thing to.
What are you writing?
I can write it over here. So here's one of the properties lines that we talked about, but I don't know if I made explicit, and it has to do with the fact that it minimizes this problem. And that's the following. Let me define this like roughness functional j of x, which you pass in a function and it'll do something like that thing. And the whole creation splines came from this observation. And that's that if you have, say, pairs xi, zi, or let's suppose you give me a function g, and when I evaluate g at the xi points, I get the zi's. So it gives me these data points, these pairs. Then I can find a spline. So then there exists a cubic spline, F, such that it passes to the same points as G, but importantly, JF is smaller than or equal to JG. So in fact, I'm remembering we did talk about this in the lecture. This is in the notes, and this is the reason why the solution to that problem is a spline, but this is the key fact. And so it's saying that if you have any points and a function that goes to those points, I can always find myself a spline that also passes to those points, but that has a smaller value of this boundary, this reference function. And so at least if you believe this is a good measure of smoothness, it's telling you to restrict attention to splines. And higher order characterization of splines, like we talked about a thin plate spline, the exact same thing holds. I just define a different reference function. So one reason you may want to use splines in higher dimensions is that if you really think that this is important for your problem, then you should be looking at a spline, because that's giving you the best bang for your buck. It's going to pass through the point. And if you give me another function, it'll pass through the same points as that function, but it'll do better with this function. So people in physics look at splines because they think about this in higher dimensions as kind of like an energy functional, and it's actually very important to them, so they know to restrict attention. So maybe one other thing to throw into the consideration. Yeah.
Sorry, I saw this in the notes and I thought like, there's a cubic spline, and so why would you ever look at any other kind?
Because if you now change this to a different derivative, then now there's a case over spline. With the property that if you give me G, it passes to the same point as G has a smaller value. So this is the most common, taking the second derivative. So that's what I was thinking.
And the number of points is in, still in.
Yeah. And the proof of this is very easy. It's all from the notes, just integration by parts. So unlike, this is a very similar result to the RKHS result we actually proved in class. Right? We showed that for the RKHS result, I can always find a representer, or a linear combination of representatives that minimizes that squared RKHS penalty, or that has a smaller value than any other function that passes through the same point. We had an analogous proof, but the proof that actually required us to understand properties of the Hilbert space, the representation from Hilbert space, like it's the spectral decomposition of these operators and stuff. And so we didn't really talk about detail, but at least we were a witness to some kind of complicated math. This is all very basic. If you know calculus, then there's nothing complicated in these proofs. They're just integration by parts. Here's the answer. So that's another question. So the answer is really, this seems to be, well, a couple answers. First is that statisticians are a slave to software. And so the cubic B-spline is like the most heavily studied thing computationally, and that's what's available in software, so we tend to use it. But the second kind of more appropriate answer is that there's a bias variance trade-off there. And so there's a bias variance trade-off not only in lambda, but also in k. Right? So if I choose k to be 9, then it's probably not going to be the case that I, in practice, have estimates that have competitive performance to a cubic spline. Maybe the variance is just too large, no matter what I choose. So k is kind of a nice middle ground.
In fact, I don't know of any practical problem anybody's ever found a cubic spline was not good enough. Maybe there's a few, but it's pretty rare. By the way, I filled in this one detail that I was very lax about at the beginning of class. Just, I mean, I hope this is very simple, but that for a multinomial, the probability that the minimum is 0, I'm sure you all know this, right? That's less than or equal to the probability that at least 1 is 0, which is 1 minus, you have to get it n tails in a row to get 0 in that category, which right is exponentially, which goes to 0 exponentially. So I felt guilty. I waved my hands there, so there's the detail for once. So the probability that you'll get something in each category in a multinomial is very high. But the probability you won't goes to 0 exponentially quickly. Not that important. I just figured I'd throw it in there.
Yeah, let me say one more thing before we answer this. If people are worried about details, like that detail on the midterm, I would say that's the last thing you should worry about. Like if you have a sense of how to solve the problem, but you're worried that this step is kind of like, well, I don't know, I'm not going to prove that goes to 0, then just write down the solution. And if you have extra time and you're feeling ambitious, you can give that level of detail, but that'll get, I mean, without that, I think we'll get pretty much full credit for the solution.
Yeah, we're not interested in testing those small technical details during the test.
Jason, you have a question? Satisfy that J ends at 0. Oh yeah, that's true, because of the fact that J ends up being, yeah.
Because if J is not 0, then from the problem, then you can, if you choose something that is random, then the minimum that is at J particularly some linear function. So
Yeah. I would say it differently, but that's a good insight, yeah.
and then J equals 0 is that at all times 0 everywhere, so hopefully we can hopefully linear or linear or something.
I think that's a good insight. So this is going back to Yusheng's question. So it basically, if K has a 0 eigenvector, or if K has an eigenvalue of 0, 1, then we can actually say that implies that this interval is 0. And that implies that interval is 0 for one of many reasons. Jesus' explanation was that if it wasn't 0, then I could just take lambda bigger and bigger and bigger and bigger, and at some point the minimum cannot be y hat equals 1. Because I'm just going to keep placing higher and higher away that penalty. It's going to exceed whatever the first term has to offer by taking not equal to 1. Another way of seeing that is that that penalty matrix, so this omega, basically this the way we got this omega matrix was through this representation, the fact that I can represent any f as a combination of basis functions with weights theta. This is just, we saw exactly the way we defined omega, so that this held. And so you can see from the properties of k that if k is a 0 eigenvector, or a 0 eigenvalue, that implies that essentially this has also 0 eigenvalue, which means that this whole interval has to be 0. Okay, so that means that this is proving the direction I told you don't need to worry about. So if you don't understand what I just said, don't worry about it. But this is just coming back to Yusheng's question, which is it's showing that this is how we prove that there is exactly k plus 1 over 2. So the problem midterm said what's the multiplicity, and the easiest way to argue is just say, oh, there's k plus 1 over 2, and there's at least that many. That's all you have to say. If you wanted to exactly pick a phone number too, this is a nice insight piece. Wow, that fun question is not the easiest one on the test. Didn't mean there to be so many questions, but I'm glad we got there.
Any last question? All right, then we'll see you on Wednesday. By the way, if you're not registered